If you're anything like me, you've been impatiently waiting for Dune Part 2 since they announced it a couple of years ago. I saw it in the cinema the other day, and let me tell you, it did not disappoint. In case you aren't familiar with the Dune universe, here's a quick rundown. Dune is a book series written in the mid-1960s by Frank Herbert. It's regarded by many as one of the best works of science fiction of all time. The first book alone is almost 900 pages long, which has since been made into a 2-part movie. The Dune universe is incredibly rich in scientific concepts like interstellar travel, personal shields based on subatomic particles, human adaptation to incredibly harsh environments, moons that tilt the rotational axis of their planets, and so much more. It got me thinking, how realistic are these ideas? Are they really just science fiction, or somewhere within the realm of possibility? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we dive into Dune to uncover how much this pioneering work of science fiction stacks up as science and how much as fiction. But before we dive into any of that, here's something that not only helps me sleep, but also helps support the channel. Manta sleep masks are designed to create a blackout effect, making sure you receive the best sleep possible. They come in a range of different variants, from their original sleep mask to their Pro for comfort and breathability. However, if you love listening to these podcasts, there's also a sound version which will help you fall straight to sleep. Use my link in the description and the code Astrum at checkout to receive 10% off your next order. Dune revolves heavily around the use of interstellar, faster-than-light travel, which is necessary given the story spans several different worlds and galaxies. In fact, the author himself notes in an appendix that there are over 13,000 planets in the Dune universe. That's a lot of planets. So let's focus on the main three: Giedi Prime, Caladan, and Arrakis. Giedi Prime is home to the Harkonnen, the current stewards of Arrakis and its resources, which we'll get to later in the podcast. It's a highly industrialized world where little photosynthesis occurs, meaning they would probably be dependent on trade with other worlds for their food needs. They've replaced almost all natural things with built environments, except for a slither of forest maintained for logging. Caladan, by contrast, is a lush, oceanic world, home of the Atreides and our main character, Paul. Water is abundant and the weather is pretty mild. Both these worlds couldn't be more different from Arrakis, where most of the action happens in the movie. Let's take a closer look. Arrakis is a desert world that makes the Sahara look like an oasis. It is the third planet from its sun, Canopus, orbiting at a mean distance of 87 million kilometers. That's about twice as close as the Earth is from our sun. If we were that close, it would be pretty hard for life to exist, given the searing hot temperatures and ultra-high radiation. So, can Arrakis support human life? It's possible Herbert drew inspiration from an actual star called Canopus, a white star in the southern constellation of Carina. At the moment, this star is in its blue loop phase of stellar evolution, where it changes from a cool star to a hotter one before cooling again. Meaning, at times Canopus could have been considerably cooler and dimmer than many yellow dwarf stars like our sun. This would have positioned Arrakis in the sweet spot of its star's Goldilocks zone at some point in its stellar cycle, making conditions more suitable for supporting life. Something I think is super interesting about Arrakis is its orbit. Just like Earth, Arrakis sits third in line from its star, but that's where the similarities end. On either side of Arrakis are two much larger planets known as the Twins. Thanks to the dedicated fans over the Dune fandom wiki pages, who have accumulated an extensive amount of information about the Dune universe, we know the Twins have elliptical orbits. These orbits pull Arrakis into a gravitational tug-of-war, which causes shifting and changing Arrakis' orbital pattern. A year on Arrakis can range from 295 to 595 standard days. I wonder if we'd ever seen an example of something similar in our own universe. Turns out highly elliptical orbits are not so uncommon. We've discovered quite a few exoplanets that follow this pattern. We also know that highly eccentric orbits can influence the orbit of other nearby planetary bodies within the same system. such as a change in orbital inclination, shifts in the orbital period, or even orbital resonance. However, I think the kind of drastic variation we see on Arrakis is highly unlikely in our universe because it would require very specific, unstable, and chaotic conditions to exist. Even then, the scenario would be short-lived. Speaking of orbits, Arrakis also has a couple of moons worth mentioning. Kreln and Arvon are both visible in the Arrakis night sky. Kreln, the larger of the two, shares a lot of characteristics with our own moon. It orbits every 25.5 days, is covered in a thin layer of meteoric dust, is speckled by craters, and has no atmosphere. Arvon is much smaller and completes an orbit every 5.7 days. While the twins affect the length of the year on Arrakis, these moons affect the length of the day by influencing how fast Arrakis rotates about its own axis. The average day is about 22.5 standard hours long. However, under special circumstances, the day can be as short as 3.8 hours and as long as 51.4 hours. Based on what we know about astrophysics, this kind of scenario seems highly improbable. Planetary rotation is mainly determined by the conservation of angular momentum. It's pretty hard to change this momentum without an external force being applied. Technically, the moon's gravities would be an external force, but it's also improbable that alone would be enough to cause such strong fluctuations in Arrakis' rotation. Similar to the dynamic between Arrakis and the twins, this configuration would also likely be highly unstable and short-lived in practice. Let's move on to two of the biggest sci-fi tropes these films deal with: force fields and interstellar travel. In the Dune universe, both of these technologies hinge on the same fictional principle, known as the Holtzman effect. I won't go into too much detail about it, but it basically has to do with the supposed repellent properties of subatomic particles. Let's start with the force fields, which take shape as personal shields in the film. We see lots of different characters using these shields during combat. They're generated around the wearer by the Holtzman effect, creating a defensive barrier that is impenetrable to fast-moving objects like bullets. Slower-moving objects like a blade, for example, can still penetrate the shield. Scientists have made numerous, mostly unsuccessful, attempts at creating force fields or invisible shields in real life. Most have so far focused on electromagnetism and plasma. We haven't looked at subatomic methods yet, so for now this will have to remain in the realm of fiction. I'm also not sure of the scientific reason why a subatomic force field would protect its user from fast objects, but not slow ones. Perhaps it was simply to move the plot along, or to introduce more tantalizing fight scenes. If the Dune force fields worked against everything, there would be no place for epic hand-to-hand combat, and wouldn't that be a shame? This aside, the shields themselves are obviously way beyond our current technological capabilities. We are only just starting to understand how subatomic particles like bosons and quarks work, and so far they seem to be incredibly difficult to predict. Even if we could predict them, it's unclear how they'd interact with matter to produce the protective barrier we see in the films. And then there's the issue of conservation of energy. The energy from the fast-moving objects that are repelled by the shield must go somewhere. You'd expect some kind of change to the shield, whether kinetic or thermal. The shields in the movies light up when hit, but it is unclear how the Holtzman effect turns kinetic energy into heat and then light. The other major application of the never-explained Holtzman effect is space folding, a key component of interstellar travel along with the spice, which we'll get to in a second. With the help of a Holtzman generator, space navigators known as the Guild Navigators can literally fold space, allowing spacecraft to travel faster than the speed of light. Right off the bat, we know nothing can surpass the speed of light without violating the known laws of physics. There are a few main reasons for this, and they boil down to Einstein's theory of relativity. Firstly, as a starship accelerates, time will begin to dilate relative to a stationary observer. As they approach the speed of light, time would effectively stand still for the crew. Traveling faster than light, then, implies some kind of negative time. And it's in going down this rabbit hole that we end up with things like the grandfather paradox and other time loop paradoxes. Secondly, a starship approaching the speed of light will also approach infinite mass, meaning you need infinite energy to accelerate past that speed. What the source of that energy would be is unclear. But from the way the director portrays it in the film, it seems the ship somehow fold space, perhaps with a wormhole, to arrive at their destination in no time at all. The second half of the interstellar travel equation is a mystical blue powder known as the spice. It has incredible economic and political importance in the Dune universe, because without it, interstellar travel would be impossible. The only way you could find this spice is Arrakis. It facilitates interstellar travel by eliciting its effects on the pilots, not the starships themselves. Let me explain. The spice imparts some pretty crazy effects to the person who consumes it. To the indigenous people of Arrakis, known as the Fremen, it is considered sacred. It has very strong anti-aging properties that helps you achieve a state of prescience by expanding your consciousness, enabling you to see the future. However, it is also crazy addictive, and withdrawal from it will kill you. The Guild navigators take this spice when piloting a starship to help them achieve that state of heightened awareness. The precognitive effects allow them to successfully navigate folded space and safely guide starships across interstellar space instantaneously. Now, obviously we don't know of any substance that can help us see into the future, otherwise the entire gambling industry would collapse overnight, but that would be the least of my concerns. Seeing into the future implies knowledge of events before they occur, which violates the laws of causality. The effect must follow the cause, not the other way around. With precognition, you get paradoxes like time loops. It also violates the law of information conservation, which says no new information can be created or destroyed in a closed system. The closest thing to the spice that might come to mind are psychedelic substances, which humans all over the world have used to connect with heightened states of consciousness for millennia. These psychoactive plants are also held as sacred by the indigenous people who use them, just like the spice is seen as sacred by the Fremen of Arrakis. That being said, there's no way eating a magic mushroom on a spaceship will make it reach the speed of light. Another sacred substance on Arrakis is water. The planet is a total desert, without any natural precipitation or surface water bodies. The only water the Fremen have access to is stored in underground wells, which they don't dare to use, because they dream to one day use this water to terraform Arrakis, make it more hospitable, and reclaim their power from the oppressive empire. The only other water source they have are the byproducts of their own bodily processes. As you can imagine, this has led to some pretty hardcore water recycling practices. You definitely notice the full-body suits the Fremen put on whenever they venture out of their underground communities. They are known as still suits, and are designed to capture and recycle as much bodily water as possible. They filter sweat, blood, urine, and other secretions through a series of microdermal layers. Once the water is separated, it goes to a collection pocket. The Fremen then drink this water through a tube, kind of like a camel pack. It sounds disgusting, but also intriguing. How would that work if we tried to build a still suit? First off, we'd need a material that can filter things at the microscopic level to separate waste from water. This actually exists. It's known as a nanoporous membrane, and it is made of nanopores so small they only allow water to filter through. Everything else that is too big, like bacteria, will be held back. On Earth, these membranes are made from a mix of materials that sadly would be hard to come by on Arrakis, namely metals, ceramics, and polymers. The second big hurdle I see to these suits is keeping them hygienic. Turns out there are a few different ways to clean and maintain nanoporous membranes, but only 2 of them seem plausible on Arrakis. The Fremen would either need to dry scrub their still suits with brushes, or apply air pressure through some kind of handheld pump. While it is theoretically plausible for us to use our existing technologies to make a very basic version of something like this, I doubt many people beyond maybe Bear Grylls and other extreme survival experts would be up for trying it out. With Arrakis being a desert planet, there's not much in the way of alien life forms to discuss. However, there is one very impressive creature that seems too big to be true: the sandworm. First off, how could a creature that big survive without much to eat in the desert? Well, you might be familiar with a similarly large creature on Earth that has found a solution to this problem. Apparently, sandworms feed kind of like blue whales. They guzzle huge amounts of desert sand and filter out the microscopic sand plankton living there. Okay, but does the maths add up? Blue whales can eat anywhere from 1 to 4 tons of plankton per day during the summer feeding season. They are about 25 meters in length and can only feed in Arctic waters, which make up 1.3% of the total ocean water. Not accounting for differences in metabolism, a 200-meter long sandworm feeding at the same rate would need about 8 to 35 tons of sand plankton per day. That's a huge number. But if you consider they have 100% of the planet's surface to feed, compared to the whale's 1.3%, I guess they could sustain themselves like that. They don't rely on water to live though, and I'm not aware of a single organism, even the most hardy extremophile, that doesn't rely on water in some capacity to survive. Speaking of water, let's talk about terraforming Arrakis. One big goal of the Fremen is to turn at least parts of Arrakis into a lush, green, and more hospitable world. That's why their underground wells are so precious to them. Any kind of terraforming would have to start with water. What I'm about to say isn't shown in either film, but it is a spoiler from the books, so if you are planning to or are already reading them, you might want to skip this part. Several thousand years in the future from when the movies are set, Arrakis is indeed successfully terraformed by the ruling powers. I couldn't find much about how this was done, but that didn't stop me from coming up with some ideas of my own. Terraforming a pure desert into a temperate climate is a super ambitious undertaking, limited mostly by time. It isn't a project you could do in a lifetime. Luckily for the people of Arrakis, the spice serves as a fountain of youth, so the time constraint is not such an issue. It makes me think of similar ideas we've had on Earth about terraforming Mars, including NASA's software system architect Casey Hanmer's idea to send a fleet of solar sails to Mars to sublimate the planet's frozen carbon dioxide and thicken the atmosphere. Another, slightly less delicate suggestion put forward by Elon Musk is to drop 10,000 nuclear bombs on the polar ice caps to release carbon dioxide and water vapor. Thickening the atmosphere would warm the planet to more Earth-like temperatures, but scientists still don't agree whether there is enough frozen carbon dioxide on Mars for this approach to work. The atmosphere on Arrakis is already Earth-like. To kickstart the terraforming process there, I'm assuming you'd need to import water from other planets. Other things to consider include soil quality, climate modification, ecosystem restoration, and overall climatic stability. You'd also have to introduce species to build and maintain varied and resilient ecosystems, which something the Emperor at the time of Arrakis' terraforming did actually do. In my opinion, Dune really stacks up to its reputation as a pioneer of the sci-fi genre. It's got everything you could want: multiple worlds, interstellar travel, force fields, weird alien creatures, and mystical powders with seemingly magical properties. Dune was never meant to be scientifically accurate. It really puts the fiction in science fiction and encourages us to use our imaginations. Fictional universes give us an opportunity to explore what we do and don't yet know, deepening our understanding of physics and get a sense of where the current limits of science lie. As Albert Einstein himself said, imagination is more important than knowledge. Knowledge is limited, whereas imagination embraces the entire world, stimulating progress and giving birth to evolution. And that makes sci-fis like Dune worth keeping around. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the movie Dune. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.